When a massive star exhausts its nuclear fuel, gravity overcomes all internal pressure. The star collapses into a region of space-time so warped that its escape velocity exceeds the speed of light. This is the classical black hole, a one-way membrane surrounding an absolute void. This model creates a conflict with the known laws of physics. If a cloud of gas with a measurable degree of disorder falls into this void, that disorder, its entropy, is seemingly deleted from the observable universe. A net decrease in the entropy of the universe contradicts the second law of thermodynamics. This law dictates that the total entropy of an isolated system must never decrease, making the inescapable void model a physical impossibility. To resolve this, the entropy of the falling matter must be associated with the boundary of the black hole. The event horizon acts as an information surface, where the data of the swallowed matter is encoded into the geometry of the horizon itself. The Bekenstein-Hawking entropy formula shows that the amount of information a black hole holds is proportional to its surface area. Specifically, 1 bit of information corresponds to approximately 1 Planck area, a region of roughly 10 to the negative 70 square meters. Because the black hole possesses entropy, it must also possess a temperature. By the fundamental laws of heat and energy, any object with a temperature must radiate. Treating the black hole as a thermodynamic body forces us to investigate the mechanism of that radiation. Thermodynamics defines a strict relationship between energy, entropy, and temperature. For any system, the change in energy is equal to the temperature multiplied by the change in entropy. By applying this to a black hole's mass and its surface area, we find that its temperature is inversely proportional to its mass. As a black hole loses mass, its temperature rises, making it a near-perfect black body emitter. Kirchhoff's law of thermal emission states that a body's rate of emission is tied to its ability to absorb radiation. Since a black hole is a perfect absorber, it must, by mathematical necessity, be a perfect emitter of thermal radiation. This radiation is not a secondary effect or a glitch in the model. It is a requirement that emerges when the rules of quantum field theory are applied to the curved spacetime of general relativity. Proving this emission exists requires us to look past the idea of a universal vacuum. We must analyze how different observers define empty space in a changing universe. In flat Minkowski spacetime, every inertial observer agrees on the definition of a vacuum. Because the background is uniform, the ground state of a quantum field is a universal constant. This agreement is possible because flat space has a global time-like killing vector. This mathematical symmetry ensures the metric is stationary, providing a consistent way to define the energy of the field and its vacuum state. In the curved spacetime of a collapsing star, this global symmetry vanishes. There is no single time-like killing vector that covers the entire history of the collapse, meaning there is no longer a globally valid definition of time. Without a consistent time coordinate, the definition of a positive frequency mode, which physicists use to define a particle, becomes local rather than global. A particle seen by one observer may not exist for another. We use a sandwich spacetime, placing dynamic geometry between two stationary regions, the distant past and future. In the past, the quantum field is an empty in-vacuum state. However, due to the dynamic intermediate space, the future observer finds this inherited vacuum is no longer their local ground state. We define the field in the initial stationary region using a specific basis of early positive frequency wave modes. This is our baseline for an empty universe. In the final stationary region, the observer must use a completely different basis of late positive frequency modes to describe the same quantum field. We translate between realities using a Bogoliubov transformation. This involves A and B coefficients mapping early wave modes onto late ones. The B coefficient is critical, mixing past annihilation operators with future creation operators. The future observer calculates the particle number as the trace of the B matrix times its conjugate. If the spacetime were stationary throughout, the B matrix would be 0.
But in a dynamic universe, the B matrix is non-zero, resulting in a positive, finite number of particles detected by the future observer. The symmetry requirements of these transformations also ensure that these particles are always generated in pairs, maintaining the conservation of quantum numbers. The math confirms that any change in spacetime geometry will geometrically generate a real flux of particles from what was previously an empty vacuum. We apply this proof to the realistic geometry of a star's collapse, as shown in this Penrose diagram. This map tracks the relationship between the black hole interior and the space at future infinity. We define past infinity, J-, as the stationary starting point, and future infinity, J+, as the destination for escaping radiation. To calculate emission, we trace an outgoing wave node from the future observer at J+, backwards in time toward the past. This potential barrier represents the gravitational curvature surrounding the black hole. Any wave traveling toward the horizon must interact with this barrier. The wave splits. While part of it is scattered away, a significant portion is transmitted directly through the dynamic region where the star is actively collapsing. This transmission directly through the collapsing matter intensely distorts the wave's phase and completely scrambles its frequency spectrum. When this distorted wave is traced back to the stationary past, it is no longer a pure positive frequency mode. It has become a mixture of both positive and negative frequencies. This mixing populates the B coefficients of the Bogoliubov transformation, proving the black hole must radiate. The final proof rests on the behavior of wave modes precisely as they graze the event horizon. Using Kruskal coordinates to avoid the mathematical singularities of standard time, we can track the phase of these waves in the extreme gravity near the boundary. As we trace an outgoing wave back toward the horizon, the surface gravity of the black hole causes its frequency to diverge toward infinity. For an infalling observer, this appears as an infinite oscillation singularity. The wave oscillates with infinite density as it approaches the horizon's edge. This divergence creates a logarithmic shift in the wave's phase. Tracing such an extreme oscillation back to the past requires a Fourier transform that mixes positive and negative frequencies. This geometric distortion ensures the B coefficients are non-zero, manifesting as the flux of particles we call Hawking radiation. The total reality of the future is split into two regions, the exterior space at future infinity and the interior behind the event horizon. In quantum terms, the escaping radiation and the particles falling into the black hole are linked as a single tensor product system. They are part of one unified quantum state. However, an external observer is restricted. They can only measure the escaping radiation subsystem. To find what they see, we trace out the inaccessible interior data. This removes trapped particles from view, leaving only a reduced density matrix. Because the escaping particles are entangled with the ones we traced out, the exterior observer sees a degraded state. The radiation appears as a mixed thermal state rather than a pure quantum state, meaning the observer has lost access to the system's underlying information. As this thermal radiation carries energy away, the black hole loses mass. It shrinks and over immense timescales will evaporate entirely. Once the black hole has vanished, the only thing remaining is the Hawking radiation, which we have already shown is in a degraded, mixed state. This outcome creates a mathematical contradiction with the principle of unitary evolution. In quantum mechanics, a pure state must always evolve into another pure state. Information cannot be destroyed. The derivation implies that the detailed information of the star that formed the black hole has been deleted from the universe, leaving only the randomized thermal radiation behind. This result, reached through the standard application of general relativity and quantum field theory, remains an unresolved crisis in physics. It is the foundation of the information paradox, forcing us to choose between the loss of information or the existence of a high-energy firewall at the event horizon.